Hello, everyone. Welcome back. Right now, we want to introduce what's called the empirical rule for a bell-shaped distribution. And so our goal will be to understand what this distribution is, how it relates to the mean and standard deviation of a population, or this distribution. And also we can use this, be able to use this bell-shaped distribution, this empirical rule, to approximate proportions of a population. Let's take a look at what this rule tells us. This is for a bell-shaped distribution. Once again, we call that because the shapes are like a bell, an old-fashioned bell. And this is true for lots of populations. So for usually people, heights of people, weights, IQs, and also other lengths of other like arms, legs, widths at the hips, other things like that also fall into these kind of distributions. Let's take a look. So if you notice, it's a symmetric distribution. So that means that your mean, median, and mode are all right in the middle. Now, if we go a certain number of standard deviations from this mean, then we'll find these kind of norms. Often we'll see it's called a normal distribution. Then there are certain percentages that tend to be between, for example, one standard deviation above and below the mean. For example, look at this one. And also to note here, this particular graph is given more for a sample where you have X bar and for your mean and S for your standard deviation. This is also true of a population where your mean we call the Greek letter mu and your standard deviation we use the Greek letter small sigma. But so if we go one standard deviation above and below the mean, so from X minus the standard deviation, X plus the standard deviation, with approximately 68% of the values of the data, that population that are within one standard deviation of the mean. Okay, so within that distance, you have almost 70% of your population typically lies within that range. Now, if you go two standard deviations above and below, so you says X minus 2S and X plus 2S, then you have approximately 95% of your population, almost all of your population within that. And then you have about 5% outside of that, either about 2.5% above two standard deviations above the mean, and about 2.5% below two standard deviations below the mean. Okay, and as you may have seen other values, often we consider those to be extreme values when they're above or below beyond two standard deviations, either above or below the mean. Often we consider those to be extreme values. And finally, if you go three standard deviations above or below the mean, that gives you almost 99.7% of your population of your data. Now, you can keep taking as many standard deviations out as you want. In fact, in some industrial and manufacturing processes, you may have heard of something called Six Sigma, where they're actually looking at 6 standard deviations above and below the mean, which is actually which includes to a very small decimal place that it excludes everything, or includes everything except a very tiny decimal value of what's left. So this is it's called the empirical rule. And it's called empirical because it's isn't so much based on theories, it's based on practice and what people see in actual population distributions. Let's take a quick look at an example then. So let's say we have this data. Let's think about the average height of women in the US. Now, the average height of women in the US, I found this value online, so it might not be entirely most up to date or accurate, but we'll use it for this. So the average height of women in the US is about 65 inches tall, and that's the same as 5 feet 5 inches tall. Now, then the population standard deviation then is about 3.5 inches tall, 3.5 inches. Now, so we're going to do then, let's actually recreate this image, this bell-shaped distribution, using these values, and we'll see what happens. All right, so once again, right here in the middle, this is our mean, this is 65 inches. Then let's go one standard deviation above and below. And also I'll draw a line for the mean. All right, so here, one standard deviation, so this is going to be This is once again is our mu, our mean. So this is going to be mu minus sigma and mu plus sigma. Now, if we add one standard deviation, this then will be 68.5 inches. And one standard deviation below will be 61.5. Sorry, it took me a second to find that. So 61.5 inches. Okay, now in terms of heights, so 68. So one standard deviation above is 68.5 inches, basically 5 feet, 5 feet and a half inches tall. And here is 61.5 inches, one standard deviation below. That's about 5 feet and 1 inch tall, almost 5'2". Okay, so what we see from our distribution is that within this range here, we have approximately 68% of women are between basically 5'1.5" and 5'8.5". Okay, about 68%. Now, if we go 2 standard deviations above and below, and once again, my drawing doesn't look perfectly symmetric, but that's okay. So mu plus 2 sigma, and that will be 72 inches. That's 6 feet tall. And then mu minus 2 sigma, and that is going to be 58 inches. So 58 inches would be 60 inches is 5 feet tall. Then that would be 4 feet and 10 inches tall. And from here to here, within 2 standard deviations, then we'd have approximately 95% of our data. Okay, so about 95% of women in the U.S. have a height or are between 4 feet 10 inches tall and 6 feet tall. Okay, so it means only about 5% lie outside that range, with about 2.5% being less than 4 feet 10 inches, and then 2.5% being taller than 6 feet. Then finally, if we go 3 standard deviations above and below, so mu plus 3 sigma, and then below as mu minus 3 sigma, then this value will be 75.5 inches tall. So that would then be about 6 feet 3.5 inches feet tall. And then here, this would be about 54.5 inches. And then that would be about 4 feet 6.5 inches tall. And here we have about 99.7%. Okay, so only 0.3% is left over. So occasionally you hear about, for example, maybe a woman on a women's basketball team who is over 6'4", 6'5", then basically that's less than about 0.3% of the population. Okay, and once again, we can do this same kind of graph for any distribution that has this shape. Okay, a large distribution, and this will come in really handy. This information is important because people who, even in ways you might not expect, for example, your width at your hips, whether male or female, is also normally distributed like this, also follows this bell-shaped distribution. And that's important for example, people who create movie theaters, who design cars, who design airplanes, because obviously all those things, movie theaters, cars, and airplanes, obviously you'd like to have as many seats as possible in a theater or a car, not a car, but especially in an airplane. But they're also, for an airplane, of course, there are also considerations of weight, but also you want to make sure that people are comfortable enough. So perhaps you want to make sure you have a seat that 95% of the people can fit comfortably enough. Basically, you can use an empirical distribution like this to determine then what those 95% of the population, what those length cutoffs are. And so therefore, they help you can actually then design, the width of a seat. And other ways you can use it like that. So this is basically what the empirical rule for a bell-shaped distribution says. And this is really valuable then in trying to use information about population successfully. Thank you. Have a good day.